Start recording. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on Twitch. And we're in the middle of some graphics programming right now, so you know what? I'm not even going to explain what we're doing. I'm not even going to say anything. I'm just going to say if you are someone who wants to program some graphics, you came to the right place because that is exactly what we're about to do, okay? We talked about bases yesterday and we got some trippy rotating nonsense happening on the screen. Because people kept egging me on to do more weird cosine, sine, theta stuff. It got a little out of hand in the Q&A, it's true, but we're back on track today, okay, to actually focus on stuff we actually care about and not messing around. Although, you know, with graphics programming, it's easy to kind of go off on a little bit of a tangent there, you know, it happens, it does. So I'm going to get right into it. Let me just mention briefly, we're on day 92, so unzip day 91 source code. If you're someone who pre-ordered the game on handmadehero.org and you're one of those folks who likes to follow along at home, unzip that source code so you'll be where I am today. Let's go to the blackboard, okay? Let us go to the blackboard because the blackboard is really where the magic happens first, okay? Because we say what we're going to do. It's like in pool where you call your shot. You know, you're like, you know, 9 in the corner pocket or whatever, and you hit it there and it goes in. That's the blackboard. Of course, there's rarely any bugs when you do. Well, there are bugs in the pool table. You try to hit it and you miss. You know, it goes somewhere else, right? That happens sometimes. Ignoring all that, let's get down to business here. So what I would like to introduce now to take the next step forward, because remember what we're trying to do here is we want rotation and scaling. Rotation and scaling, right? We already have something that blitz stuff to the screen, but before we do anything to try and make it faster or do anything like that, we have to make sure that we have the actual features that we need, and rotation and scaling are features that we actually want. Now, what do I mean by that? Well, what I mean by that is our artist, Yangxian, right? She draws some stuff, and the stuff looks pretty awesome, right? It's like the little dude, the hero or something. She draws that in a bitmap, and then that bitmap, we have code right now that will display that bitmap on the screen anywhere we want. But it has to be exactly the same as what she drew, okay? There's no, we can't do anything to it right now. Literally nothing, in fact, right? So all we've done is something that basically does a block copy of some memory to another location, and we've only implemented one thing, right? Which is alpha blending, right? We did implement alpha blending, and that's the thing that allows us to kind of mask away all of the stuff in the bitmap that's supposed to be transparent, so that when we blit it, you know, stuff can show through. Like if there's a tree back here, you know, it can show through or whatever, right? So we did that, and that's good. But what we'd like to be able to do is we'd like to be able to do various effects on these things as we blit them. And there are several that we might find important for compositing, for getting the most out of the stuff that Yangxian draws for us, right? And so one of the things that we'd like to be able to do is we'd like to be able to scale these things and rotate them, right? Scaling is useful for a number of reasons. It's useful for effects, like if we want, you know, let's say we drew, maybe she draws like some smoke or something, right? And we want that smoke to start tiny and like get bigger, right, as it animates or something. That would be scaling, right? Or maybe we want something like she draws like some little throwing star weird thing, right? And we want it to throw across the screen, but we want it to rotate as it does so, right? So we want it to spin, right? And so what we'd like to be able to do is just take art assets that our artists make, and we'd like to be able to apply arbitrary rotations and scales to them. And there's other things that we'd like to be able to do too, like for example, we might want to colorize these, like for example, change the colors from red to green to whatever, right? There's other things we might want to do that are pixel operations, but in terms of geometric operations on the shape of the thing, we at least want to be able to do these two things because they're going to be important for allowing us to animate stuff in the way that sort of gets the most out of our artwork. Because remember, artwork is expensive, right? Whether it's in terms of money, if you're paying an artist, or time, if you are the artist, it takes a long time to draw good art. And so what you want to always be thinking about is, how can I make programming things that will get the most bang for the buck out of the art that I have? Because no matter what you do, your game will get better. No matter how much money you have, your game will always get better the better code you have to get that art onto the screen, because you can always do more with whatever it is that you had, right? All right, so how do we do this rotation and scaling? Okay, well, let's start with something very simple. Let's start with the first step of the process, okay? Let's just talk about what pixels are filled, okay? So what we did yesterday is we figured out how to, do simple bases, right? Where we could sort of say, all right, we've got a coordinate system and we could rotate that coordinate system. And so we made something that was pretty straightforward, that was basically a thing that would allow us to draw like little squares, right? And we could rotate those squares around, okay? And if you remember, in fact, I'll just go ahead and run it here. Why don't I? Let's just run it. Let's go nuts. You know what I'm saying? Let's not, why do we have to always be so serious all the time? Really, you people, you're just bringing me down. Let's lighten up a little bit. Let's go ahead and run the game. All right, so here's this this ridiculousness that we made there, right? It was totally crazy. And the reason it was totally crazy is because people kept egging me on to change stuff in it when we were in the Q&A. It was relatively sane originally, but then, it just got out of hand. And so what happened was people started adding these weird, I did it, but, people were egging me on, like I said. So let's clip away all this ridiculousness. Let's just cut it out for now so we can see the original thing. None of this weird wobbly stuff. None of this craziness, right? Let's try to get back to something reasonable, okay? Let's just go ahead and get it back to where it was before we started the craziness, right? And now you can see that it's just, one more thing. Negative x-axis dot y, x-axis x. Do we have everything proper here? I think so. Why are we still collapsed? That's like our y-axis doesn't actually have a length to it. Oh, because it's 100 times. Right, we don't need to do that. It's already scaled. There we go. So this was our little coordinate system, and you can kind of see us rotating it around here, right? And we put a little 4x4 grid of points in there so we could see that they all rotate with it, right? And so all this was showing was how we create a coordinate system that can rotate and scale, right? Because we can scale it as well, right? Like if I do that, you can see it gets larger, right? And if I do that, you can see it gets smaller. So we can multiply it by whatever we want to scale it, right? But that only tells us how to work with points, right? That tells us how to compute points on the screen that are rotated in scale, but we don't actually know how to do like what we want to do, which is take a bitmap, right? That's this rectangular bitmap and rotate that and scale that onto the screen, right? And so the very first thing we're going to have to do is do something a little fancier than what we're doing there, right? We got to do something a little fancier because what we need to know is when we're on the screen, right? Here's these pixels, right? This is our screen with all the pixels on it. We can't just have something that tells us, okay, we did some rotation and scaling, and here are those points, right? That we wanted to compute. We computed the points, so we can rotate and scale them around, right? What we actually want to know is if we were to rotate and scale an entire rectangle, right? What would we actually fill on the screen? What are all the pixels that would actually be included in that rectangle, right? You feel me on that one? See where I'm going with that? That's what we need. That's our next step, right? So essentially what I want to do today, if we can have enough time to do it, I want to change this into something that draws a solid rectangle that's rotating and scaling, right? Solid. Because that's the next step in our process. We basically have two steps, right? Make a solid spinning thing, and then fill it with the correct colors to make that texture. There's a bunch of other stuff along the way, or rather that come after that to sort of tighten things down, but that's the basics, right? So how are we going to do that? Well, do you remember our collision detector, right? Do you remember collision detection? We sort of started talking about a lot of the things that we would need to do when we were talking about the collision detection, because collision detection and rendering are actually not that different. They both involve substantively the same sorts of operations, and specifically pixel filling has a lot to do with collision detection, because think about what I'm asking. If I think about this pixel as a point, and I say, is this pixel something that I should light up for this scaled and rotated rectangle? Well, what is that if not a point inside rotated and scaled rectangle test, which is collision detection? It's saying, does this pixel hit this shape, right? And so really all we need to do is extend our collision detection understanding a little bit past where we did it. And in fact, if we had done the collision detection to handle rotation, we would already know everything that we need to do, but we haven't yet. And so, we gotta sort of, this is the first time we'll be into it, but we'll be able to then go back to our collision detection later and use this, what we've learned here, to make it better, right? Okay, so what I want to suggest to you is that let's suppose that I just want to know if a given pixel on the screen, given by, let's say, its center point, if that center point falls within a rectangle. And I'll make it easier for you at the moment. I'll simply say, well, let's suppose temporarily that you don't even have to worry about rotation and scaling. I'm letting you off the hook there. All you have to do is for a rectangle that is aligned with the screen, and here comes my, pixels or whatever, right? There they are. For a rectangle that's aligned with the screen, tell me which of these are in and which are out, right? Distinguish between these ones that overlap the shape, right? Here is the shape, and these ones that don't, okay? Now I hope that after this long in Handmade Hero, you would all be able to tell me the answer to that question. What you would say to me is, well, okay, if I have a minimum x, right, and I have a minimum, and a maximum x, right, and I have a minimum y and a maximum y, right, like so. And again, I'm using this coordinate system for now, but it doesn't matter, whichever direction it is, doesn't matter. If I have those minimums and maximums, right, you should be able to tell me for a given pixel, if this is an x and a y, right, does that overlap or doesn't it, right? How would you do that test? Well, I hope you would say something like, all right, if the x is greater than or equal to the x minimum, right, and, right, we'd say and I guess I'll write it in C++ version here, right, the x is less than the x maximum, right? And remember, we did that sort of inclusion rule so that things that abut work properly, right? If it's greater than or equal to the minimum, meaning it's on this side of the minimum, and it is less than the maximum, meaning it's on that side of the maximum, right? Then it's in for x. And furthermore, I could do the exact same thing with y, right? It's greater than or equal to the minimum and, right, less than the maximum. This complete test here would tell me if a pixel was inside or not, right? So for any given pixel, I could just check, is it greater than the minimum bound and less than the maximum bound for each of my two axes, and then I would know. Hopefully that makes perfect sense. Hopefully that's something that should be relatively straightforward to you if you've been watching all of the episodes. If you haven't, well, go back and watch them, I guess. Very, very simple stuff, right? Very, very simple. So now the question is, well, you know what? I'll take it one step further. So I could write something that actually fills these pixels for a rectangle that is not rotated and scaled, right? I could write something by just iterating over all pixels on the screen, right? All of them, and doing this test, right? That would fill it. So, you may say that's very inefficient. Well, you're right, it is inefficient because we'd be testing all the pixels even though we don't need to, right? But we could make it much more efficient by just doing all the pixels, in some conservative bound, right? Right? We could say, well, we know that the rectangle is roughly in this region of the screen, so we'll just iterate over those pixels. And then our wastage would be very small, right? And furthermore, because it's a aligned rectangle, we could even go, well, okay, we actually know exactly what pixels it fills, so we'll just only iterate over those pixels. And then this test would not be necessary, right? And that's the routine we actually wrote, right? That's the routine that we wrote before. When we did draw rectangle, what we did is we just pre-did all of that checking and decided to only loop over the pixels where we knew the test was already true. But we didn't have to do that, right? If we couldn't have produced that minimal bound, we could have just iterated over some wider set of pixels, a little bit more than we needed to, right? Or even the whole screen if we wanted to. And inside this loop, checked to see whether X and Y were inside and only colored the ones that we should have, right? We could have done that. And in fact, let's do it. Let's just prove that that's true, right? I'm going to take this thing, this coordinate system call that we've got here, and this is just going to be our little play thing, because since it's not something we actually ever need to use, let's actually write a function that literally does draw rectangle, but it does draw rectangle in the least efficient way possible, okay? So here's our draw rectangle. We'll call it draw rectangle slowly, let's say. Here's our buffer, here's our min and max, and here's our colors. It takes the exact same parameters as the other one, and off we go. We start off with exactly the same loop, and we say, okay, we're going to start at the buffer memory, and instead of advancing it to the min x and the min y, we're not gonna. We're just going to start right there. And we're going to go through every last pixel on the screen. Make sense? So here we go. We've got our buffer. We're going to go, I forget what these are actually called. I think they're width and height. Oops, that's supposed to be height. There's width. And so I'm not going to try at all to do anything smart here, right? I'm not going to try to cull or anything. I'm literally just going to say in here, for every pixel, I'm going to test to see whether it's inside or outside, using exactly the thing I just wrote. X should be greater than equal to my minimum coordinate, right? And it should be less than my maximum coordinate on X. And then the exact same thing should be true for my Y coordinates, right? My Y should also be in range. If it is in range, I will set the color of the pixel that we're on. If it is not, I will leave it alone. Okay? So very, very straightforward. Oops, I've got to still build that color by doing the smush down here. So there we go. And why not? I'll make this a V4 since we previously, we now have that capability. I'll just go ahead and put in that so this routine's a little more modern, right? Okay. This will be our color 32. There we are. So that draws rectangles extremely slowly, right? And if I want to, I can take that coordinate system thing that we did before, right? Where we do the y-axis and all that sort of stuff. When we go to draw one of those, instead of drawing the weird grid pattern stuff that we did there, well, you know what? I'll still draw it, right? But instead what I'll do is I'll just draw a rectangle that's at that location, and I'll use the x and the y axes to kind of move out to compute that min and max, right? So what I'll say is we'll draw a rectangle slowly. We know what the color is. We'll turn this off. Don't need that now. We'll turn that off. So what we want to do is say, okay, we're going to draw from the origin, right? And we're going to draw from the origin to that min and the max, right? So we're going to say entry origin plus entry x-axis plus entry y-axis, and that's going to be our maximum, okay? And so we just need to pass it the output target. We need to pass it the color, and then we should be good to go. And of course, let me see, did I forget anything there? I don't know if I forgot anything there or not. Let's see, so output target, entry origin, I need to add the entry origin, there we go, because I need the minimum and the maximum, so that should do it, right? So in theory, I believe, well, there's one thing that we didn't quite do there. So I got to stop it rotating first, because when it rotates, we're not actually taking the min and the max, so I got to make it so it's actually stable, if that makes sense. So I can't, we got to make sure that our angle for at the moment is not going to be anything, it's just going to stay stationary. There we go. And so I think that's too large, so I feel like our axes, were our axes getting scaled somehow here? Because it shouldn't be, maybe I've got a bug in my draw rectangle slowly. It should be only filling a smaller region than that. If x is less than vmax x, y greater than, let's see, blah, 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 blah. Pixel equals row. That looks correct to me. Vmin x, vmin y, vmax x, vmax y. The x's and the y's look right there. Our axes should be pointing straight up and down, so that should be fine as well. So yeah, I'm not seeing why that's wrong. Hold on one second. Sorry, it's important to get this part right, because that way we won't have to deal with it in the other one there. So if I add the x-axis, I go over in x. If I add the y-axis, I go up. That should have given us a valid minimum location there. And in fact, what I could do too, I would like to do this just so we can see them. I'm going to draw these after the fact, like this. I'm going to draw these in a different color. So I'm going to draw these in some kind of color that's a little bit easier for us to distinguish from the one that the other thing's drawing in. So we're just going to go ahead and do this, like so. I want to be able to see those points on top of the rectangle. V2 dim, there we go. Okay, so that is where we are in pixel space, and for some reason our rectangle is not properly clipping to its max bounds. Of course, I don't actually know for sure that the max is where the max says it is, so I do also want to just quickly make sure that I've got that. So I'm going to do a thing here where we just draw that max in, that max location, like so, Vmax, I guess. So I'm going to compute that by saying Vmax, here it is. So that way I can see where it is and make sure that it's not an incorrect value. Yeah, so it's not, my Vmax computation is somehow incorrect. Oh, because I added it twice. Boy, it's a typo dated it. There it is. All right, that should have worked the first time, but we were passing the wrong parameter. So yeah, all right, it's a typo day. What can I say? All right, so back to the point at hand. Now that we actually have this, you can notice that this fills the rectangle correctly, right? We have the rectangle there. And we're not doing it in an efficient way because we're filling the entire screen, but it's okay in terms of correctness, right? We're filling the rectangle that we want to fill by just doing a pass over the entire screen. And you can see draw rectangle slowly here. Literally, it checks every pixel and just sees which of them are inside, right? Which of those are inside the pixel, right? And so what I could do, again, like I said, is I could say, you know what, I'm going to restrict the area that you march over to something smaller than that, right? And then we would just restrict these to something smaller, and we would only test a fewer number of pixels. We could go all the way to only testing the ones that we need to test, which means you don't have to test at all, but same deal, right? All right, so that's all good. And so you may ask, all right, how does that help us do our rotation and scaling? Right? How does that help at all? We're basically just back to where we started, only we're much slower. Well, the answer is these right here, think about what these are doing, okay? What are these ands? What are we actually computing? What we're saying is, for any given pixel on the screen, we are making sure that the result of a series of 4 edge tests all comes back stating that we are on the inside of whatever that edge is. Right? We are first testing against xmin and saying we want to make sure that we are on this side of that edge, right? Or on it, as the case may be. For xmax, we're saying the same thing. We want to make sure that we're on this side of that edge, right? Same with ymin and ymax, right? Same with ymin and ymax. So the question is now, well, if we wanted to rotate this, couldn't we just do the same thing, right? Can't we just test against 4 corners of our rectangle, and if they all come back true, we know we're inside? The answer is absolutely we can. So instead of thinking about it this way, let's just change this to a slightly different format. Let's say is inside, right? Or better yet, let's just say edge test, right? And we'll take that first one, right? So we'll take whatever this is. This is 0, this is 1, this is 2, this is 3. We have 4 edges to test against, right? Edge test 0, we want edge test 0 to come out true. We want edge test, right, 1 to come out true. We want edge test 2 to come out true. And we want edge test 3 to come out true, right? We want all the edge tests to come out true, and if they all come out true, we assume that we are inside, okay? So all we would need to fill a rotated and scaled one is some way of producing an edge test for our rotated and scaled rectangle. Now, before we get to any fanciness here, I'm going to show you how you could have done that without my help. If you have watched all of Handmade Hero, you already know the answer to this question, okay? Let's make the construction. Here is that basis of our rectangle. Here is the one of the points, right? Here is another one of the points, and here is the final point, okay? Right? So I want to test against these 4 edges. Well, I only need to make code that tests against one edge, and then I can call it 4 times, right? So we're only looking at one problem here, and that problem is given one edge, let's say this edge right here, right? So I've got P0 and P1, right? Or I could think of it as having the actual edge there, right? In fact, maybe we do that. I've got P0, and in this case, this was my x-axis, right? I'm sorry, that would be the y-axis. Why am I so... I seem to do that a lot here. I mix up the x's and the y's. All right, so this is that origin, right? This is the origin, and this is the x-axis, right? And I want to test to see whether we're on this side of it. How would I do that? So I told you already about the perpendicular operator, right? So it would be free for me if I wanted to, for example, to produce a vector perpendicular to the x-axis. Now, it turns out that I don't even really need to do that, right? Because we know that the y-axis is perpendicular to the x-axis, correct? So we know that this vector here, perpendicular to the x-axis, we know that that's just the y-axis. We already have it, right? Very, very straightforward. So if I wanted to know if a point somewhere in the world was on this side of it, how would I do that? Anyone know? Remember, we've already done everything you would need to be able to do this, to answer this question. We've done it on Handmade Hero. So the answer is the dot product, right? The dot product, the inner product, we covered it. That is all that we would really need to do this, right? Because if we have this vector, right, if we could take P and subtract the origin from it, we end up in the exact classic dot product scenario. We have a base, we have 2 vectors, we have the one that goes to P, and then we have the edge that we're testing against, right? We have its perpendicular, which is the perpendicular to the edge, right here. All we need to know, if we want to know which side of this edge P is on, is take its perpendicular and do the dot product. If that dot product, again, that maps P onto here, it tells us how far along this we would go. If that dot product is positive, we know that we are on this side of the edge. If it is negative, we know that P was over here. So the sign of that dot product will tell us which side of the edge we are on. And it's trivial for us to compute. It's just inner product, right, of P minus the origin. It's just the inner product of that with our perpendicular, right? And our perpendicular in this case, we already know it is. We don't ever have to compute them. If we're testing against this x-axis, we know that it's going to be the y-axis. If we're testing against this upper limit to the x-axis, we know it's the negative y-axis, right? So on and so forth. So it's really, really simple. This is the entire edge test that we would need. That's the only thing we would need to do to determine whether or not a pixel was in. We just do that 4 times. We do that 4 times, and we're done, right? And all we need to do is check the sign of it. We don't even need to know what its magnitude is. We don't need to compute anything other than, was it going to be positive or negative? And we just want to see if it's positive. That's it. So the edge test is just, is it greater than 0? And we can flip it. We can choose which way we want. We can choose whether we want these normals to point in or out, right? We can choose which way we want to frame it, right? Because we can instead use the negative y-axis there, right? We could do whatever we want there. So let's just implement one of these as an example, right? Let's just implement one of these. Okay. So here we go. Let's suppose that I start this rotating again, right? It's not rotating right now. I start it rotating again. And now we got a situation that's kind of nasty, which is basically that we only actually are able to fill our rectangle, in this kind of lame way, right? Because it's really just filling it to whatever this point is here. It's trying to fill a rectangle between these 2 points. So when this point is in the positive direction, it works, and at other times it doesn't because our edge tests all fail, right? So all we need to do now is change from those bad edge tests that were just totally for rectilinear ones. All we need to do is change it to using edge tests that are actually based on the 4 points that we actually have, right? And we could do them for arbitrary 4 points actually if we wanted to, but I'm going to do them for the rectilinear ones because that's all we actually care about. Since we're not going to be filling arbitrary shapes in Handmade Hero, we just need to rectilinear bitmaps. All right, so how do we do that? Off we go. let's go back to our draw rectangle slowly. So here is our v min. So what we want to do now is change this draw rectangle slowly to actually take maybe all the things, right? So we've got our origin, we've got our x-axis, we've got our y-axis, right? And now we want to go ahead and fill that. Now we could just quickly verify that stuff's getting passed correctly if we wanted to. We could go ahead and say that we're going to compute v min from these, right? There's our v min, there's our v max, origin plus x-axis plus y-axis, like so, like that. And then we go down to draw rectangle slowly. Draw rectangle slowly. Rectangle slowly. And instead here, when we pass that, we will actually pass entry x-axis, entry y-axis, right? And then that color. And now we should see, in theory, exactly the same thing happen, right? Meaning you can't fill anything until that comes down to the positive. It could fill, and then it goes away. All right, exactly what we would expected. So back up to draw rectangle slowly. Here we go. When we are drawing the rectangle slowly, we now need to say, let's test these edges as they actually were using the edge test that I just described. All right. So first off, we need to test, test each of them. And so I'm just going to actually record here what the edge functions were so that we can see it in a little more detail, right? So I'm going to do an edge 0, edge 1, edge 2, right? Edge 3, like so. And then, like I said, all we need to do is test that all of the edges are actually in. And so what I could do here is I could actually sort of do a version of this, right? I could do the version of this that is the same as what we're doing now, because if you think about it, these are sort of like dot products, right? This is like saying, well, I'm just taking the x-coordinate. I don't need to dot it with the x-axis because I mean with the x-axis because I already have it, right? I already have what its value is. So I'm just testing it against the min, right? I could phrase that differently by saying I just want to know if the x minus the x min, right, is positive. Right? That's like doing that sort of rebasing, putting it around, I'll be 100% explicit here, just so you can see what I'm saying, right? We can rephrase these edge tests, even in the rectilinear case, to be much closer to what we expect by saying, okay, before we had an x min, right? And we had an x, right? And we wanted to know, well, was it on this side? So what we were doing is we were just writing the test explicitly. We were saying we want x to be greater than or equal to x min. But that is the same thing as actually doing the dot product effectively, right? It's the same thing as saying, all right, take x and subtract x min from it. You will now get a positive or negative value that tells us which side we are on, right? And then we can test to see whether it's greater than or equal to 0. Right? So we could have phrased it the other way, we just didn't because it was so simple, we didn't need to. So we can turn it around in a slightly different way. We could do it this way and say, all right, we want x minus v min, then we want x minus v max dot x. We want that to be less than 0. We want y minus v min. Oops, some parentheses in there. We want y minus v min to be greater than 0. And we want y minus y max to be less than 0, right? Again, same exact thing happening. All I've done here is just change those into stuff that looks, right, like this. I did the p minus origin, and then I did the dot product with the perpendicular. Doesn't need to happen because they're already in the perpendicular coordinates, right, x and y. We're not rotated at all, so we don't actually need to do this part. But this part we had to do, right? So that's all I did. Right here, I did it. Now what you'll notice as well is because we're not doing the dot product, the sign doesn't flip, right? And so that's why these are different comparisons here, right? What would normally be happening is we'd be testing against normals that were in different directions, right? Those perpendiculars would be pointing in different directions, so we could always test greater than or less than, right? But we're not doing one here, so it doesn't actually reverse it, if that makes sense. So that's why we have to do the different ones there. But we can easily go ahead and sort of fool that, right? What we can do is say, all right, let's suppose we want to make greater than be our standard. So everything's always going to be greater than, right? Like so. So I want to change all these. So if I do edge 0, edge 1, edge 2, edge 3, I want them all to just be using the same comparison, right? I want them all to be using like that comparison, let's say, or something, right? So they're greater than. And maybe, you know what? It probably makes more sense to think of these as pointing outwards, you know, because that's the way you normally think of surface normals pointing. We'll get to that sort of stuff a little bit later, but let's make them point outwards. So let's say that we want positive means you're outside the shape, negative means you're inside the shape. Let's just use that as our convention, right? So I want all of my edge functions to actually be negative. I want them all to be negative, and so in order to do that, I have to reverse the sense of some of these, right? Every other one, the edge 1 and the edge 3 are going to be wrong because they were based, or you know, they're going to be the opposite of the other two, right? So in this case, x minus xmin.x, I want that to actually be a reverse test. Because before, that was giving me a positive answer on one side of x and a negative answer on the wrong side, right? And so I need to flip the sense of that. So again, it's just a simple negation, right? Just flip it. Same thing true of v min y, right? And the other ones were already producing negative values when they were on the correct side of the edge, so those are just fine, right? And so this gives us, again, the exact same results as we had before, but we're one step closer. We're one step closer, right? So there we go. We're super close. All we have to do now is lever up one more time and actually get the dot product in there, right? Because remember, I said we want inner product, right? We've got our inner product. We want to do our inner product after doing the rebasing, okay? So let's do that. So here's our origin subtraction, right? Reversing it back to the same way it was. And now we just have to make synthetic edge values, right? Things that point in those directions, okay? So we've got our vmin, right? Here's our xmin, right? So the edge that we want, we said we want pointing outwards, right? So I'll clear the diagram so we can be completely clean. We want our edges, our perpendiculars pointing outwards, right? So here we are on the minimum. What is that vector, right? Well, that vector is pretty simple. It's just negative 1, 0, correct? Pretty simple. The one for the x max is just 1, 0, right? Same thing here, right? We've just got this is negative 1, 0. Oops, this is 0, negative 1, and this is 0, 1, right? So it's totally trivial what those edges actually are. Our perpendiculars actually are. We can just read them straight off the diagram. Okay, so edge 0, again, I said was negative 1, 0. The max version was 1, 0, right? Again, minimum here for y and maximum for y. Okay. Oops. And of course, in this particular case, we have the problem that the inner is going to do the full dot product. So I really need to do essentially like, okay, I've got my pixel p, right? And it's the xy coordinate of that pixel, right? And I need to then say, okay, it's technically going to be the pixel p minus, you know, the v min, pixel p minus the v max to do that full sort of vector subtraction, right? The pixel p minus the v max. So again, they're just producing one that's based off of whatever that location is. So for example, when we want to do this one, we have to subtract whatever the point is from this, because that is what we're testing against, right? So there we go. Almost, there we go. So there we go. Now we're actually doing the full test, right? And you'll notice we got a lot slower because it's doing a ton more operations for every pixel on the screen. It's going to get worse before it gets better, people. We're going to be super slow for a little while before we get better. But you can see that it's still doing the same thing now, but it's doing those edge tests, right? And then finally, all I have to do is now actually change these edge tests to using actual edges of the rotated thing, which again, hopefully you've seen is pretty straightforward. There's not a whole lot that we will have to do there to do that. So let's just go ahead and create those. We have the x-axis and the y-axis. So let's think about what these would be. Here is my x-axis. Here is my y-axis. So if I want to test against this first edge, we'll treat this as our first edge. Actually, you know what? Let's treat this as our first edge. Because I keep saying x's and y's backwards a bunch of times. So let's try and not say x's and y's backwards. I'll do my best. So here's our origin, right? So what I can do now is just say, okay, the pixel this stuff here, this vmin, vmax, we're just going to get rid of. There's no more vmin and vmax. So now we're just going to use the origin, x-axis, and y-axis stuff. All right. So the first thing we need to do is say, OK, where's my blackboard? Let's test against this edge here. So that's the x-axis. It's going from the origin to like the one, along the bottom, right? In our case, it's the top because that screen coordinate system's actually flipped, but it doesn't matter. It doesn't, any space, all this math still works no matter what the space is, right? So we have the origin. We have the x-axis that's running across here. What we want to do is say, is it on the correct side of this, right? So we want to use the negative y-axis would be the perpendicular, right? The negative y-axis. So our first test is going to be against the negative y-axis, that dot product, right? And we're going to use the origin as our basis because that is a point that runs through this edge. So we can, again, make sure that we put P in the same space to test which side it's on, right? So we just say P minus the origin. That's our first test, okay? Next, we'll test against this guy right here. Now, this base point, to do that test, that's going to be the origin plus the x-axis, right? So we actually need to do the origin plus the x-axis for the base point that we're going to test off of. Okay, and then we need to say which is the axis that we're going to test. Well, we want it pointing outwards. That's the x-axis that points in that direction, right? So that's just the x-axis. All right. Next, we'll do this guy. Okay, and so that's that Vmax point that we're based off of there. Essentially, I'm just going around this counterclockwise, force of habit as a graphics programmer. So the test of the axis is going to be the y-axis there, right? So that's going to be the y-axis test, and the point that we're on is going to be just the origin plus the x and the y-axis, right? So there's the origin plus the x-axis plus the y-axis. That's the point we're on. And then finally, our final edge coming down, right, is going to be this, which is just, the origin plus the x-axis. I'm sorry, plus the y-axis. And you can tell which one it's going to be because we haven't used it yet, but it's going to be the negative x-axis, right? It's pointing out in that direction. Okay. So there we go. Now, if I can compile that, you will now notice that without actually really changing anything about what we were doing, just following it step by step, we are now filling a rectangle, right? And we're filling the rectangle with rotation and scaling just fine. We can do anything we want to that, and it would just go ahead and work, right? You could see it rotating there, but if I wanted to, I could go ahead and introduce some scaling to it, right? By just going back to that code. Let's see here, Handmade CPP, yeah, here we are. If I wanted to introduce some scaling to it, again, I could do sort of the same thing that we were doing yesterday by just saying, let's put in some notion of a change in scale that happens over time. And you can see that that works fine, right? Now, again, we're very slow right now because we're not doing anything. We're not even compiling with optimizations on, so we're like the slowest we could possibly be. We're filling all the pixels on the screen. So what we might want to do is say, well, okay, let's at least, we can do a little bit better than that without actually, just algorithmically, we can do something smarter there, right? Because what we could do is we could say, well, we know very trivially that the only pixels that could possibly be involved in this, right, are bounded by the minimum and maximum x and y values of those points, right? I mean, if I come in here and I have some rotated shape, right, and so it's got 4 points, right? Well, I know that no pixels outside of this this oriented rectangle, right? If I just take the minimum and maximum of all the points, I would end up having all the pixels that could possibly be filled. So I could restrict my choice of pixels to just those, and then we wouldn't have to fill the whole screen, right? We'd fill a much smaller region. So that's a good first step to what we should do. So let's just go ahead and do that, right? That's very, very simple for us to do. So in this render group here, right, I'm just going to introduce the same things we had before, right? I got an int ymin, an int ymax, an int xmin, and an int xmax, right? I've got those. And all I'm going to do here is first I'm going to set them to be exactly what they were before, right? Ymin, Ymax, so xmin, x max, but I am going to change to saying that we will actually consider whatever that max actually is, right? So we'll actually test all of them, because now our inclusion and exclusion is going to be based on these tests, not on this. This is just pixel coverage, right? And so I'm going to say, all right, buffer, oops, buffer width. And so that's all the pixels on the screen again. So if I compile this, we get the same result, and it's still quite slow. But what I can do now is I can say, all right, let's go ahead and introduce something that actually tries to get the min and the max out of this, right? So I've got 4 points, essentially, that I could have for minimums and maximums, right? So I've got essentially 4 points that are the points of this weird rotated shape. I've got the origin. I've got the origin plus the x-axis. I've got the origin plus the x-axis and the y-axis, right? And I've got the origin plus the y-axis, right? So I've got 4 points. So what I'd like to do is just loop through those points, and I'd like to go ahead and take I'd like to shrink it down so that they sort of fit around that guy, right? So what I'm going to do is say, all right, let's say we loop over these, int p index equals 0, p index is less than array count p plus p index, right? And what I'm going to do is I'm going to take that p, make a test point out of it, p index, and I'm going to say, all right, I want to now take the y min, the y max, all those guys. I'm going to say if, well, you know what I'll do first. I don't actually need to do that. We'll do int px and int py, and these are just going to be the floors and ceilings of those values numerically, right? I have a floating point value. I want to see what its closest real value is, right? So I believe we have these in our handmade intrinsics, right? We've got floor, yeah, and ceil. So here's our floor and our ceiling. So we'll do our pxf, I guess, or we'll do floor, something like that. Floor x, ceil x. That seems good. So yeah, that seems like the right thing to do. So b to p test p equals p index. Sorry, I'm getting a little tripped up here for a second. All right, so there's my floor x and my ceil x. I'm gonna take the 10 minutes that I started late because we're right at finishing this part up, so we might as well. So there's the ceil, and then I've got the same things happening in y, like so. And so now that I've got those, this is sort of like the min x, the max x, and that sort of thing for this guy, right? So this is the test min x and the test max x and so on that this guy would represent. And so all I have to do now, and in fact, I don't really have to take this, the floor and ceil in that way. I could just say that the ceiling of y is the floor y plus 1, right? Because we know that they're on either side of each other, but I'll leave it that way for now. So now all I have to do is say, well, if the y minimum, right, if the minimum y we've seen is actually greater than that floor y, right, then I want to assign them, right? I want to accept the new floor y as my minimum, right? And again, all I'm doing is just, again, gathering up sort of the minimum and maximum so that we know what we actually need to test against. And similarly, I'll expand the maximum to go ahead and encompass that whole area, right? So ceil y, ceil x, like so, right? And so that'll actually grab those, and then all I have to do is actually go ahead and make this, excuse me, start out the opposite way, right? Like so. So now we're starting essentially as big as possible, right? We're starting with we're starting with nothing included, right? And we're just kind of moving the x-min back and moving the x-max back as far as possible. Now this could still produce things that were off the screen. So at the end we do have to clamp them. We have to say if the x-min, you know what I should probably do? I should probably do some kind of a width thing here, like width masks or something like that. Max, like, I don't know, width max, something like that. Height max, just these values so I don't have to type -1, right? It's like the inclusive version. So that's width max and that's height max. And Yeah. And so all I really have to do now is just finish clipping those. So I say if xmin is less than 0, then xmin equals 0. If ymin is less than 0, then ymin equals 0. If xmax is greater than widthmax, then xmax equals widthmax. And the same is true for y, height max, right? And these are floor sealed. There we go. All right. Oh, but of course that didn't quite work. Hold on one second. I have to. We're almost done. I just got to fix a couple things first. So just double checking. We've got our width max and our height max. I want to do something quickly, which is just to not test the edges. I'm just going to always fill, right? So instead of this, I'm just going to always fill so we can see where our bounding region is. So I'm going to say, all right, everywhere in the bounding region that we use, we're going to fill. And then now we can test our bounding region. So we start xmin off at the maximum possible value it could be. And then as we step through each of these points in our index, we floor them so that we base and seal them so that we know what their floor and ceiling values are. We then go ahead and say, if the xmin that we currently have is greater than whatever the floor is, then we are going to accept the new floor value. And then that will basically keep moving xmin down as we go. Same with ymin. So as we find lower ymins, we accept lower ymins, right? And then similarly, if the xmax is ever less than whatever the ceiling was, we accept that. Oops, and there's our typo. Knew there was going to be one. And so there we go. Although, why are we still up in the corner? We're getting our range. Oh, because now, right. Now we have to restore our buffer pre-step, right? Because we have an actual min x and min y. So we're going to have to do this again to step to the correct location. So there we go. There's our xmin. Oops. There's our xmin, and there's our ymin, right? And now you can see we are correctly picking the rectangle to test. And so now if we re-enable our test, we get our correctly filled guy, and it's still not a fast fill, but it's much faster than it was. Now we have a ton of stuff still left to talk about. We are not home free, but again, like I said, I'm out of time. We're now just about running into where 1 hour's worth of code. We've got a bunch of stuff to talk about, like subpixel stuff and what pixel centers are, and a bunch of other things about sort of finicky stuff in there. And there's a bunch of things that we also didn't talk about. We can go in and simplify a lot of these. Like we don't need to do these expressions exactly the way we did them. But I'd like to go ahead and wait. We'll pick back up here tomorrow and clean a bunch of this stuff up as we move towards actually getting our full blitting working. So there you go. Let's go to the Q&A. Like so, and I will, I will start taking questions now. Please prefix your questions with Q:, and please try to keep them to what we're doing. If you want to ask off-topic questions, stuff like that, please come back before the stream starts, because that's really the best time to do that sort of stuff. I tend to skip anything that's off-topic during this so we can concentrate on just questions about what we're working on. T7 Samurai, what are your computer specs? So this computer is super old, but at the time it was like a fancy Xeon. So it's kind of a little bit tricky to talk about its performance because it's not the kind of performance that you would get on it's one of those things, right, where you're kind of in an unusual scenario. Like most users don't have Xeons, right? So it's a W5580, which, and I think it's about 5 years old. I think maybe 6 years old. It's about 5 or 6 years old. So it's a very old processor, but at the time it was a Xeon, so it's got like a bigger cache than most things do and so on. So it's not probably as fast as most of the computers that people are probably following Handmade Hero on. But either way, like I said, we're not really dealing with performance yet. So you know, any computer probably can do what we're doing here, though, because even though we're doing it super inefficiently, it's just not much to do, right? It's just one little rectangle. So. Is it weird that I got really excited once the rotated fill got faster? No, that probably just means you should be an optimizer guy, right? If you're not already. That means you'll be kind of excited as we do our performance stuff, I guess. I mean, basically getting excited when stuff like this happens is what determines whether probably you're going to be a good programmer. Because if you're not excited about this sort of stuff, you probably don't really want to, you shouldn't be a programmer, right? You should do something else because you want to do stuff that you're excited about, the little things about it, right? That's what makes, I'm assuming what makes a great basketball player, I mean, besides physical build or whatever, right? And programmer does that too. You got to be, have a good brain for it or whatever, right? But what determines that you're going to go do that thing is like, you're going to be a great basketball player if you love the feel of shooting a basket, right? Because you're going to sit there and do it all the time and you're getting really good. And so, yeah, I mean, that's kind of how that works. Would skewing the axes still work? Yeah, it would. So if you wanted to skew the axes, that probably would still work because as long, well, so no, if we wanted to skew the axes, we couldn't take the shortcut that I took, which is using the axes as the perps. You would have to actually compute the perps. Because if we skew the axes, then they will no longer be perpendicular to each other. I'll show you what happens if you do it. But it would be really trivial to support it. You just actually compute the perp, right? So if you skew the axes, excuse me, skewing the axes was this, right? Y-axis equals, cosine angle plus something that wasn't 90, right? And so can you kind of see what's happening there? Do you see how that's going? You get this kind of, I'll try to skew the axes even a little more maybe than they were before, so it's a little more pronounced, that effect. Do you see what's happening there? You end up in this situation where basically like that perpendicular is not perpendicular anymore, so you're not actually getting the proper test. If you wanted that to work, though, it's not that big of a deal. We can go in and add a more proper perpendicular, right? So to do a proper perpendicular, I already showed you how to do that. And I said there's even, let's add a perp operator right here, right? And so let's do that. I mean, that's not, I don't mind doing that in the Q&A because I already explained it all in a different one. So let's do that, right? Let's do perp x-axis, right? Like that. And so in Handmade math, right, .h, in here I can just add one of those. That's an easy v2 operation that's just inline v2 perp v2a. And in here we just have literally just that result, right? It's just v2 equals whatever the negative thing is, like that, right? And there's that perp. Makes sense? So if we did that, then if we do this here, we've actually added the perp operator. Oops. v2 result. There we go. So once we have that perp, we can go ahead and tackle this guy a little bit better, which is that in here now, instead of doing this, we would actually always use the perpendicular of the other axis. So we would essentially say, okay, we don't actually want the negative x-axis. What we want is the negative perp of the x-axis, right? We don't want the negative y-axis, we want the negative perp of the x-axis. We don't actually want the x-axis here. What we want is the perp of the y-axis, right? We don't actually want the y-axis here, we want the perp of the x-axis. We don't actually want the negative axis here, we want the perp of the y-axis negative, right? And in theory that should work, although, is this going to be backwards. I got to think about that. So let's think about, well, the fact that it's not filling suggests that it is. So let's just double check. Okay, so what we want here, right, is we've got this is the origin. This is the x-axis point when we step out to it. And so what we want here is we want the perp of the x-axis, right, which is going to go this direction. So we want the negative of that. Negative perp x-axis, that's correct. We then are here going this way on that y-axis, so we want to test that, which is going to be, so the perp of this is going to be pointing that way, so it's the negative perp of the y-axis, right? So it's actually that, right? And then we go this way, we want the thing pointing that way, so that's going to be, again, for that x-axis, that's just going to be the perp of the x-axis. So we just, yeah, so oops. So it's the negative y-axis, negative x. So that's the way that it would be, right? And so once you do that, it'll work just fine. So you can't take the shortcut that I took before, but if you don't take that shortcut, and really, so you know, I'll put the to-dos in here so we don't forget. But this is what I was going to do next time anyway. Perp dot product, so perp inner, simpler origin calcs. Is downscaling bitmaps correctly slower than, is downscaling bitmaps correctly slower than upscaling? More color points to blend. Well, it depends what you're, it depends how. The answer in general is yes, but it may not be as yes as you think. So the answer is that typically nobody downscales bitmaps more than 2x. What they do instead is they use MIP mapping. So typically, and we'll be doing this on the stream, although I don't know that we'll actually need MIP maps, but we'll be doing the downsampling part. So typically what happens is this, right? So let's say I want to downsample this bitmap, right? So I want to make it smaller. And what I want to do is I want to take this block, right? And I want it to become a single pixel. So I've got, you know, something like this, right? And so on. And I'm doing a 2x scale on the two axes. So basically these four, right, map to here. So this A actually takes its values from all of these things, right? So what I need to do there is I need to sample 4 pixels, right? And I need to produce, I need to average them together or do some other filter to get that A. That's a very simple, it's called a box filter, right? So that would be downsampling, right? Now, if I was upsampling, I have to do the exact same thing, right? To upsample, what I need to do is I need to again sample these, but instead now I'm producing many A's from it, right? So instead now this is going to, let's say I'm upsampling by 2, right? Well, now I need to produce this region, and so the A's all fall in here, and what I do is exactly the same thing, right? To compute this A, or maybe this one's a better example. To compute this A, right, I need to get all 4 of these and then compute the sort of a weighted blend between them that produces that sort of, you know, oh, it's a little bit more towards this guy than the other 4, right? You know, that kind of thing, right? So upsampling and downsampling are exactly as expensive when you're only talking about between, you know, 0.5x and 2x. They're doing exactly the same thing. The problem comes when you have a greater than 2x factor of shrinkage, right? So you're doing like 0.25x or something, right? But the way that video cards and everyone else do this to get around that problem of, well, okay, if I wanted to downsample like this, you know, this thing, and I'm downsampling to just 1 pixel. So I got to do the whole map. I want to downsample to 1 pixel. It's a super tiny stretch, right? I've got to read all these guys and produce this 1 pixel, right? Or something like that. That may seem like a lot of work, but it isn't, because what they end up doing is they just create MIP maps, which are pre-filtered versions. So for every bitmap, let's say you have a 256 by 256 bitmap, right? They actually pre-compute a 128 by 128, right? Then a 64 by 64, then a 32 by 32, then a 16 by 16, then an 8 by 8, then a 4 by 4, then a 2 by 2, and then a 1 by 1. And what they do is they say, how far down am I scaling this? If I'm scaling it from its normal size all the way down to, say, 30 by 30, I will pull from the MIP map that is close to that, the 32, so that I know I'm still only sampling 4 pixels for any pixel that I draw, right? I don't have to sample some giant region like of this thing. I'm just sampling one little 4x4. And the reason I say that it's still more expensive is because typically what you do is called trilinear filtering here. And what trilinear filtering does is it samples from both the next highest and next lowest. So it samples 4 texels from each of these to produce this guy and blends the result together. And the reason for that is to prevent any noticeable popping as you transition between them. Eventually, will you implement anti-aliasing into the rendering of the rectangle, or is that too much for the CPU? Actually, so the answer is yes, we will be implementing it, but no, we don't actually need anti-aliasing of the rectangle. I don't want to explain why quite yet, but the reason is because since we are pulling from alpha bitmaps, it turns out that we'll get anti-aliasing for free. So we don't have to use multi-sampling. If you are actually drawing actual shapes whose edges are visible, that's when you have to worry about that anti-aliasing. And just to be a little more concrete on that, what I mean is to say here is, if we are blitting a bitmap that has a border of 0 alpha around it, we get anti-aliasing for free as part of our texture sampling. Our texture sampling actually handles this for us. Texture sampling handles the anti-aliasing, and we'll show how that happens when we go there. But if we were actually drawing shapes, so if we were actually drawing a solid rectangle that didn't have any alpha, then we don't have that texture sampling to save us. And that's why graphics cards have things like MSAA or multi-sampling, right? It is not to anti-alias bitmaps. You never need MSAA or any of that stuff to anti-alias bitmap blitz that have alpha in them. What you need it for is the edges. So MSAA and that stuff only actually works on the edges of things. It's the only place you actually need it to do stuff. And so the way that that works is it takes many samples inside a pixel of the edges that pass through them, right? And then uses that to sort of smooth that edge. But we don't have any edges because we are always blitting bitmaps that have a contour that's defined in the alpha channel. So we don't ever have to do this. So fast or no, we just don't have to care. We are going to be doing this texture sampling because we need that for quality, and so the anti-aliasing will just be baked into that and we'll get it for free, which is nice. None of what I just said would have been true if we were rendering 3D shapes that had contours defined by polygons, right? Then that's when this comes in, and we're fortunate that we're not doing that because yeah, that would be a whole thing that the CPU would have to do. All right, no more questions? It's a pretty hilarious little shape we made there. Believe it or not, I mean, what has it been, 2 days or something? Believe it or not, we are just not far from having rotated and scaled bitmaps. In fact, we might even have them tomorrow. It depends on what order we tend to do things. Like, I might show you how to get the rotated and scaled bitmap first, but it's kind of janky, and then we'll go back and do a pass over all of the math to show, okay, how do we make sure we're always subpixel accurate? How do we make sure we're this? How do we make sure we're that? But like I said, this stuff ain't that hard once you kind of know how to do it. It's actually real simple. It's just building up all this knowledge of how all these things work and having them introduced to you in a reasonable way is most of it. Once you actually see it, you're like, oh, I mean, you saw what I did. It was not that complicated. It was not that much more complicated than just filling a rectangle that was aligned with the screen, right? Real simple. All you have to do is just make that small step of okay, let me define some other edges, and there we go. Now, again, it keeps layering on top of each other, and would you have known to do all that stuff if it wasn't for 30 years or 40 years of graphics researchers figuring all that stuff out? No, right? But they have figured it all out, and so the nice thing is we can just kind of keep, leveraging all of their work to very quickly go, oh, okay, here's how we do it. We're good to go. Orlando Bloom, historically, did we ever do anti-aliasing with CPU rendering? Well, that is a very good question, and I don't know the answer to it. I mean, obviously we've done anti-aliasing and CPU rendering for some definition, for a certain problem domains, right? But if you're talking about game software rendering of 3D stuff, I don't know. I really don't. It's not actually that expensive, probably, to implement. Like, oddly enough, I don't know that MSAA would really actually be all that expensive in software. Like, it's expensive, but you only pay for it at actual edges, because anything that has a complete coverage, you don't actually ever compute the MSAA for it. So it's really just more of a sort of an edge complexity thing. How many edges are there in the scene? How many pixels have edges passing through them, right? So I don't know. So I think it wouldn't be that expensive. I mean, usually the expensive thing is texture sampling, right? And we're going to see that. Like, texture sampling is presumably, I would suspect, texture sampling is going to be the reason why we can't really use our software rasterizer to ship the game, right? We're never going to get that as fast as the GPUs have it, and that's why you use GPUs for a 2D game. It's that ability to pull the textures through. The writes are probably not as big of a deal. I mean, yes, the GPU does a better job of that too, but we could probably get around that by tiling. We could probably get around that, right? So the real killer is that texture sampling. And so MSAA, if we had to implement that, which we don't because we won't have a use for it, because we don't have edges. But even if we did, that probably wouldn't be the biggest deal. I bet MSAA really wouldn't be that big of a deal for us, because the texture sampling would probably still dominate our runtime. That's just my guess. So, all right, looks like we're done with on topics. So I'm going to postpone anything more till tomorrow, when we will talk about, you know what, I think we should just keep the trend of just like getting the first thing going and then go back and revisit. So I think maybe we'll do it in two ways. What we'll do is we'll just get a janky bitmap fill going. So we'll fill this with an actual texture, like we'll map the guy's head in there or something. We'll do that tomorrow and Friday or whatever. And then next week what we'll do is we'll start on going through and cleaning up all that math, so that everything's just so, and we can be pretty happy that things are in the right place before we start any optimization work. But yeah, good work today, people. Good work today. We filled a rotated scaling shape. And another thing that we didn't quite mention, but that might be worth mentioning is this will work for any convex shape, right? That inclusion test, that idea of checking all the edges and seeing if they're all inside, any convex shape, that'll work. So we could actually have an arbitrary n-gon, essentially, as long as it's always was convex and didn't have like any, in notches cut into it, basically, it would work. And if you want to, you can even use the same sort of a test to do something for concave shapes. It's just, again, we don't need those for anything, so I'm sticking with the stuff that's the most acceleratable, because you always want to do the fastest thing you can for the thing that you need. All right, so I'll go ahead and wrap that up here. Let's close things down. Let's go ahead and save our mischief board. I don't know how big that file's gotten. Probably pretty big, huh? All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It has been a pleasure coding with as always, and I gotta be honest with you, software rasterizers are just so much darn fun. Collision detection is always a nightmare. It's always bogged down when we do collision detection. When you do rasterization, it's just so much fun. Like, I had a blast yesterday and today doing the coding was just fun. And pulling the bitmaps tomorrow is going to be a blast. I hope you'll join me for that. 5 p.m., same time, same place. We'll go ahead and do that, and I think it'll be a lot of fun. What is it? Oh, it's Thursday already. I said Thursday and Friday. Oh, man. So we've only got an hour. We've got an hour to do bitmap sampling tomorrow. All right, we can do it. I think we can do it. I don't know. We'll see. I'll think about it. I'll give it a little thought. between now and then and see if I can align the things I need to teach in just the right way so that we can make sure that we fit it in an hour. If not, maybe we go long. Maybe tomorrow's the day we go long. Because we wouldn't, an hour or two, I think we'll be able to do it. So anyway, I hope you'll join me for that. It's been a lot of fun. I think it'll keep being a lot of fun. So I'd love to see you back here tomorrow for that. Anyway, if you want to follow along at home, of course, and check out some of the stuff that we've been doing, you can always pre-order the game on handmadehero.org. It comes with the source code as we do it every day, so you can download it and play with it just like I did on the stream and do whatever you want to do to kind of learn more effectively by trial and error, basically, right? So if you want to do that, you can pre-order it here. We also have a Patreon. If you want to support the video series, you can always subscribe to that. It's much appreciated. And we have a forum site where you can ask questions as well. There's also community ports to Linux and Mac and stuff like that there if you want to check those out. And we have a tweet bot that tweets the schedule at you. So if you want to catch the video series live, that is the thing to subscribe to. It will tell you every day. It sends out in the morning when it's going to be and then an hour beforehand. So it always gives you a big heads up. All right, thanks everyone for joining me. I will see you tomorrow, hopefully. If not, have a wonderful weekend, and I'll see you on Monday either way. So take it easy, everyone.